You ever wonder how something like a jet engine, a medical implant, or even the phone in your hand gets made so perfectly? Well, it's not magic, that's for sure. It's actually a hidden science, the science of measurement, that makes sure everything fits, works, and is safe. And it all kicks off with a really simple question. So imagine this. You design a flawless object on your computer, a perfect 3D model. You send it to a fancy, state-of-the-art 3D printer. When that part finally comes out, is it an exact 100% perfect copy of your digital blueprint? The answer, believe it or not, is always no. And that little gap, that tiny difference between the perfect design and the physical reality, well, that's right where our story begins. You see, it doesn't matter what process you use. 3D printing, machining, molding, you name it. These tiny, microscopic variations are always going to sneak their way in. This creates that gap between the plan and the final part. And the biggest challenge for pretty much every high-tech industry today is how to find, measure, and most importantly, control that gap. So that leads us straight to this fundamental idea in modern engineering, what I like to call the illusion of perfection. We're surrounded by technology that promises incredible precision. But the reality? Oh, it's way more complicated than that. Here's the truth. No physical object is truly flawless. I mean it. If you could zoom in close enough on any surface, you'd find a whole landscape of tiny little imperfections, slight deviations in size or shape or texture. Perfection is the goal, the ideal, but it's not a physical reality. Okay, so if these little flaws are basically inevitable, the challenge completely shifts. It's not about avoiding them anymore, it's about finding them. And this is where manufacturing turns into a kind of high-stakes detective story. We're hunting for invisible flaws before they can cause some really, really big problems. So what exactly are we hunting for? Well, these are our main culprits. We're looking for dimensional inaccuracies. You know, a part that's just a few microns too big or too small. We're looking for geometric deviations, like poor circularity, where a hole isn't a perfect circle, or a surface that isn't truly flat. We're also searching for things like surface roughness, hidden voids inside the part, and even tiny misalignments when you put it all together. Now, you might be thinking, a few microns, who cares? Why does all this matter so much? Because in critical stuff, we're talking jet engines, medical implants, radiotherapy equipment. These microscopic errors can have absolutely massive consequences. A tiny flaw could lead to a catastrophic failure. Reliability isn't just a nice-to-have, it is literally a matter of safety. And this is where our hero finally enters the story. To fight these invisible flaws, engineers and scientists have an entire discipline, one that is completely dedicated to this exact challenge. That science is called metrology. And no, it has nothing to do with the weather, that's meteorology. This is the science of measurement itself. Metrology gives us the official rulebook and all the tools we need to quantify that gap between the design and the reality. And a key piece of that rulebook is something called geometric dimensioning and tolerancing, or GDNT for short. You can think of it like the official legal language for an engineering drawing. It doesn't demand perfection, because that's impossible. Instead, it defines the acceptable limits for every single feature on a part, how round a hole has to be, how flat a surface must be. It's the standard that everything gets measured against. So, how in the world do you measure the invisible? Well, you're going to need a seriously high-tech toolkit. Forget about your tape measure or calipers. We are talking about some truly amazing machines. First up, we've got the workhorse of any quality lab, the Coordinate Measuring Machine, or CMM. If you need to verify a part's geometry with mind-blowing accuracy, this is your go-to tool. It's basically a hyper-precise robotic arm with a super-sensitive probe that gently touches the part at thousands of points, recording the exact X, Y, and Z coordinates for each one. Then, software stitches it all together to create a perfect digital map of the real-world object. But a CMM, it can be a little slow, especially if you have complex, curvy surfaces. For sheer speed, we turn to non-contact methods like 3D optical scanners. These things project a pattern of light onto an object. Then a camera captures how that light bends and deforms over the part's surface. And from that distortion, powerful software generates a massive 3D point cloud, capturing millions of data points in just a few seconds. So right there, you see the trade-off, don't you? The CMM gives you that incredible, undeniable precision, which makes it the gold standard for verifying critical geometric tolerances. The optical scanner, on the other hand, gives you incredible speed, which is perfect for capturing complex shapes in a flash. Engineers have to pick the right tool for the right job.
But what about the flaws you can't see from the outside? The ones hiding deep inside a part? This is where we get into some serious superpower territory with X-ray computed tomography, or XCT. It is, and I'm not kidding, a CAT scan for industrial parts. It takes thousands of X-ray images from every possible angle and reconstructs them into a full 3D model, showing you everything on the inside without ever having to slice the part open.
This technology is an absolute game changer, especially for the world of additive manufacturing. Why? Because with 3D printed parts, some of the biggest dangers can be hidden deep inside. XCT is often the only way to find those internal voids, to measure complex internal channels, and to verify the part's structural integrity, all without destroying it. But what if you could stop a flaw from ever even forming in the first place? That's the whole idea behind in situ monitoring. Instead of waiting to inspect a finished part, you actually embed sensors right into the manufacturing machine to watch the part as it's being made. This lets you catch and correct deviations in real time, which means you can prevent a bad part from ever being finished. Pretty smart, right? So we have all these incredibly precise tools, but what if I told you that not a single one of them can give you a truly perfect measurement? This is the kind of mind-bending secret at the very heart of metrology. Absolute perfection is impossible, and the real experts, they don't even try to achieve it. The core principle, the whole philosophy of modern metrology, is this. Every single measurement, no matter how sophisticated the tool, has a tiny margin of error, a small range of uncertainty. So the goal isn't to do the impossible and eliminate it. The goal is to know exactly what that margin of error is, to quantify the uncertainty. So when a metrologist reports a dimension, they don't just hand you a single number. They give you a value, plus or minus a calculated uncertainty. They aren't guessing. They are defining a precise, known range where the true value is guaranteed to exist. And the crucial thing to understand here is that this is not guesswork. We are talking about highly sophisticated statistical processes. Scientists use powerful simulation methods to account for every possible source of error, from tiny temperature changes to machine vibrations, to calculate that final uncertainty value. This is what gives them the statistical confidence to say, yes, this part is good, or no, it's not. Okay, I know this all might seem incredibly technical, but I promise you, it connects directly to the safety and reliability of the world all around us. So let's bring it all home and talk about why this obsession with precision really, truly matters. The science of metrology. It's what ensures that a medical implant fits perfectly. It's what ensures a radiotherapy machine delivers the exact dose of radiation, and that every single part in an airplane engine performs exactly as it was designed to. It guarantees the integrity of massive structures and the quality of the next generation of 3D printed products. At its core, it's the hidden science behind trust. And that leaves us with one final thought to chew on. We are constantly inventing these incredible new ways to build our world. But the challenge that will always follow is this. How will we invent new ways to trust the things we build? The ongoing quest to answer that very question? Well, that is the science of metrology.